Okay, we're going to go ahead and start, and I hope you can all hear me on this, and we're going to continue our discussion on chemistry. Are there any questions on anything at this point?
You said that the lab test for lab would be on the 14th.
We will, let's see, let's get into screen and go into chemistry. And if I remember correctly, rid of that, bring it up there. There we go. We were ready to start talking about chemical reactions. And with a chemical reaction, oh, got a comment here. Sound still isn't working. Can you hear me at least? Okay, good. Let me see what I can do here. Hang on a second. Okay. I'm going to try and turn on the speakers here one more time. I thought I had it the other day, so let's and it's still okay. Pardon me while this is thinking about what it wants to do. Okay, well, while it's working, I'm going to go ahead and start, and I'll try to get this fixed in the middle of class. So chemical reactions, as long as you can hear me, then, okay, oh, we got something here. This might have something to do with it. Okay. Okay, I don't know if it's working or not, but as long as you can hear me, that's all that matters right now. If you have a question until I can get this thing fixed. Okay, thank you. As long as you can hear me, we're good. And if you have a question, just shoot it through chat and I'll answer you. Okay, chemical reactions. We're talking about mixtures and compounds. Mixtures are different than compounds. Mixtures are just the physical mixing of ingredients. You know, if you, as I said, I may have used the analogy of setting up a fish tank. You pour sand in the bottom of the fish tank, and then you add water to it, and the sand and the water all mix together, and it gets very cloudy. The sand's floating in the water, but eventually the sand settles to the bottom of the tank, and the water's above that, and it's all clear. That is a mixture. It will, there's been no physical change to the ingredients. The sand is still sand, the water is still water. You know, when you are pouring a sidewalk, for example, there's the properties of the sidewalk, the sand, the gravel, the cement, forming the concrete, they can all be separated. Even though they form a hard surface, you can still break them apart and get the individual components. With a mixture, there is no chemical change to the ingredients. But in a compound, it's different. There is a chemical change taking place. A chemical reaction takes place. It causes bonds of the different molecules to change, to rearrange, to break, or to build up. And so whenever you have a chemical reaction, you're doing something to the bonds, and the bonds are all based on electrons. So you're doing something with those electrons. You're rearranging electrons to create a new type of bond. Whenever you have a chemical reaction, you have reactants. You start with reactants, and then you end up with a product. For example, you've probably at some point played with baking soda and vinegar, or saw someone that did and made a baking soda volcano, or maybe you made one yourself. And if you mix baking soda and vinegar, you get a very nice foamy reaction with lots of gas given off and lots of little bubbles popping everywhere. And it looks very much like a volcano erupting. And lots of people do it in science fair projects in middle school, or that's always a good middle school science fair project. And you get these the bubbles and everything else coming off of that. That's a chemical reaction. You started with baking soda and vinegar as the reactants, and the product is carbon dioxide, sodium chloride, and water. That's what you get when you mix baking soda and vinegar, because vinegar is acetic acid and baking soda is a base, and acid and bases will neutralize each other. In this case, it gives off lots of CO2, that's the bubbles, and it will give off plain water, and it will give off salt. And that is the product. The reactants in a chemical reaction will always combine to give you a product. And the product is different from the reactants. In the baking soda volcano, the reactants were baking soda and vinegar, acetic acid, and the products were carbon dioxide and water and plain ordinary salt. And okay, now it isn't like you mix sand and gravel together. It is different. Now, a good example of a mixture of a compound is baking a cake. If you take a cake mix and you mix in the cake mix with the flour and the sugar and the flavorings, and you add in eggs and oil and whatever else you add into it, and you mix that all up, and then you put it in a pan and stick it in the oven at 350 degrees for however long you bake it, a chemical change occurs to those ingredients. You can no longer look at the cake and say, well, there's where the egg is, and there's where the sugar is, and there's where the flour is, and that's where the flavoring agents are. It's all one uniform substance. The product, the cake, is completely different from the reactants. The reactants have changed to give you the finished product. So the reactants will give you products that are different than the reactants. And it usually requires energy to get that to take place. Now, when we look at a compound, we use formulas. We use a molecular formula. We've all heard of water. We know that water is referred to as H2O. We've all said that for water, H2O at some point or another. Excuse me. H2O is a molecular formula. It indicates 2 hydrogens and 1 oxygen. Glucose, which we'll talk about an awful lot in here, is written as C6H12O6, which means 6 carbons, 12 hydrogens, and 6 oxygens. The number of the individual atoms is always indicated by a little number there. How many individual atoms you have in a molecule in a compound are indicated by the number after the letter. Like the C for carbon is 6, the H for hydrogen in water is 2, H2O. And they are held together by bonds. They're held together by some sort of electron-based bond, whether it's like an ionic bond, like in sodium chloride, or a covalent bond in glucose or water, or maybe a hydrogen bond that we see between water molecules, for example. All the bonds are caused due to electrons. Now, let's when we have a chemical reaction, there are three types of reactions that take place. The first one is called the synthesis reaction, where we take simple atoms or molecules and combine them to give us a larger, more complex molecule. And this, a synthesis reaction is also called an anabolic reaction. Anabolic reactions require the use of energy. Go back to my example of baking a cake. You mix the flour and the sugar and the salt and the eggs and the oil together and mix it up and bake it. Now, at the point where it's all mixed together, you could still theoretically filter out all those ingredients. It's still a mixture at that point. Once we apply energy to it, it becomes a compound. And so now, and it's a totally different substance than what it was before. The cake substance has more calories per gram than the individual components of the oil and the water and the sugar and the flour and whatever else you use to bake the cake. This is an anabolic or building up reaction. When it's a synthesis reaction, we take small molecules and turn them into large molecules that are complex. You know, we see this when we are going to store sugar in our liver as glycogen. We take simple sugar molecules and link them together thousands at a time, and we produce this compound, this mixture, this compound in our liver called glycogen. You know, glycogen in our bodies is like starch to an apple or a potato. The bulk of the potato is starchy. Well, plants store their large sugar molecules in the form of starches. We store it as glycogen. Now, the second type of reaction is the decomposition reaction. Decomposition reaction is where we break things down. You know, we take a large molecule or a large compound and reduce it to simpler forms. We call this this decomposition reaction gives off energy, and we call it a catabolic reaction. We break bonds. Anabolic reactions build bonds and require energy. Catabolic reactions break bonds and give off energy. If you light a candle, that's a catabolic reaction because you are taking the energy stored in the paraffin, the wax of the candle, and you're releasing that energy, and you get heat and light, and the candle shrinks. And the end result, in this kind of reaction, the reactant is the paraffin, and the end product is going to be the release of carbon dioxide and water and heat and light energy. So you're going to release energy here and give off carbon dioxide and water vapor. Every time you burn something, whether it's a log or a candle or a piece of paper or gasoline, the end result is usually going to be the release of energy and carbon dioxide and water vapor. So that's a decomposition reaction. An exchange reaction occurs when you have both an anabolic and catabolic process. Now think about this. You're not only, you're building something up and tearing it down. If we were to eat a piece of chicken, which is mostly protein, we would break that protein, that chicken meat down. That's a decomposition reaction. We break the protein down to its individual amino acids. The amino acids are the primary structural component in protein. Proteins are made up of amino acids. But we don't destroy the amino acids. We turn around and take those amino acids and use them to build proteins that we want. The chicken protein's fine for a chicken, but we want human protein. So we take the amino acids from the chicken meat, from the chicken protein, separate them out and then rearrange them in the pattern that we want, because the amino acids are all the same. There's only 20 amino acids. We use the ones from the chicken and build our new protein. We build up our skeletal muscle. Or it might be beef protein, it may be fish, it might be animal protein or plant protein, it doesn't matter. The amino acids are still the same, and we use those to build our proteins. So there's an example of both a catabolic reaction breaking things down and an anabolic reaction building things up. That's an exchange reaction. Now, another type of reaction that we see in our bodies is known as the reduction oxidation reaction, or redox reaction. When something is burned, oxidized, you're burning something, burning a log, burning a piece of paper, lighting a candle, lighting a match, burning gasoline, we say that the material, the compound, is being oxidized. It is going to give off energy. It's going to give off heat and light, or at least heat. And it's going to release energy, and it's going to give you carbon dioxide and water. So we say that the material has been oxidized. When it's oxidized, it loses electrons. It loses electrons. When you burn a log, you're releasing energy and you release electrons. Those electrons are going to get captured by something else. We don't like to have electrons running loose in the universe. So whenever we release an electron, it has to be grabbed somewhere else. And usually it's oxygen that's going to grab those electrons. So we say oxygen gets reduced because it's gotten more negative, it's gotten more electrons, and the wood or the gasoline has been oxidized. It's given off electrons that go to the oxygen. And so in our bodies, when we oxidize glucose, we use oxygen to grab those electrons, and we end up giving off carbon dioxide, the very carbon dioxide that we're breathing out, and we give off water vapor, and we have energy temporarily contained within this molecule, what we call ATP. It's what our bodies use to carry energy around. It's sort of like a battery for us. Okay, now, a lot more in that later on. So if you are a chemical reaction, you're one of two types. You're either exergonic, where you give off energy. Exergonic reactions are catabolic. You eat something, and you look at, you ate a Snickers bar with 180 calories in it. That's a measure of the energy in the Snickers bar. Maybe you don't like Snickers bar, maybe you like Milky Way. Doesn't matter. They all have calories in there. Calories are the measure of all the calories represent the measure of all the potential energy in all the covalent bonds in that particular food. Whether it's a Snickers bar at 180, or an apple at 60 calories, or a slice of bread at 90 calories, that is a representation. That tells you exactly how much energy, how much potential energy is held in the electrons that make up the molecule, that are attached to all the atoms in all the molecules that make up the bread, or the Snickers bar, or the apple, or the potato. And so with an exergonic reaction, you're going to give off energy. It's going to be a catabolic reaction. You're going to break down the carbohydrates in the bread, or in the apple, or in the Snickers bar, and release energy and release electrons. Endergonic reactions absorb energy. They use energy to build for chemical reactions to occur. The product ends up having more potential energy, like baking the cake. Baking the cake is an endergonic reaction, because you're taking all those electrons from all those different molecules and combining them into one product, and it has a higher calorie content, a higher energy content than you started with. There's more energy in the finished cake than there was in the eggs, or in the oil, or in the flour, or in the sugar. So the finished product has more energy than we started with. because it has the energy combined from all the other reactants. Endergonic reactions endergonic reactions contain energy. Exergonic reactions give off energy. Think exit, exergonic, releasing energy. Endergonic reactions, entrance, retain energy. And an endergonic reaction is anabolic. We start with little things and we end up with a big product. Now, a chemist will tell you that chemical reactions are reversible. Whatever we do on once, if we take the reactants and we get a product, we can take that product and reverse it back to the reactants. Well, in chemist world, you can, but in the human body, we can't. We can't because we're dealing with very small concentrations of substances. We're not dealing with large amounts like we would in a chemistry lab. So we have very small substances to begin with, and we usually use up the products of the reaction immediately. If we break down sugar and release energy from that sugar, and we end up with carbon dioxide and water and ATP molecules, that energy's been used. And we breathe out the CO2 and we breathe out the water vapor. So the reactants are gone. Chemical reactions in our bodies are generally not reversible because we've gotten rid of the products already. We've used them up. So for us, a chemical reaction isn't reversible. And there's some other things that apply to chemical reactions. In a chemistry lab, if you heat up a solution, the chemical reaction that you might be watching is going to go faster. Chemical reactions tend to go faster at higher temperatures. I mean, consider if you're going to make sweet tea. You put a pot on the stove and you heat up the water and you add the tea bags to it. And when do you add the sugar? Do you add the sugar when it's all cooled down, or do you add the sugar when it's hot, when the water's hot? You add the sugar when the water's hot because it will go into solution better. So because the water molecules are moving faster and they will allow the sugar to be spread out quicker and go into solution easier. So the rate of reaction making sweet tea goes faster at a higher temperature. If you try to put sugar into tea at room temperature, or cold out of the fridge, what's it going to do? It's going to settle in the bottom of the glass and you get sugar sludge in there. And while some people like that, my grandma used to love making, having a little tea with her sugar because she'd put so much sugar in the glass and try to stir it up. But, temperature affects the speed of reaction. Things go faster at higher temperatures. If we increase the concentration of the reactants, usually the reaction goes faster too. If some is good, more is better. If some is good, let's add some more to it and it'll go faster. Like your baking soda and vinegar volcano. If you add a lot of vinegar to it and it's not doing anything and you throw in a lot more baking soda and you get a great reaction, well, that's good. You've increased the amount of the reactants, and so the rate went faster. And then the last one here is the size of the particles. Smaller particles can react faster because there's more of them. Little tiny particles run into other little tiny particles and a reaction occurs at a faster rate. Large reactants have a hard time. You wouldn't take a 10-pound block of sugar and try to put that into a 1-gallon container of tea to try and sweeten tea. You would put in powdered sugar, granulated sugar, little tiny pieces of sugar, little tiny granules of sugar, because it'll go into solution a whole lot better than one big giant block of sugar. Size matters here. The smaller is better. Now the problem is that none of these things apply in the human body. we can't raise the temperature of the body to increase the rate of reactions. We are pretty much limited to 98.6, 37 degrees Celsius. So the chemical reactions in our bodies have to happen at body temperature. We can't turn the temperature up to make things work better. The concentrations are usually extremely tiny, and we aren't going to bring more in, so we don't have the ability to increase the amount of reactants to make it work better. And with particle size, we're always dealing with extremely small particles, so there's nothing we can do about the particle size. So none of these three characteristics of a chemical reaction apply in the human body. Well, what we do have is something that doesn't show up everywhere else, and that's a catalyst. A catalyst is a substance that can make the chemical change, the chemical reaction, go faster. A catalyst can make a reaction in the body go faster. And the catalyst that we use is what's known as a biological catalyst called an enzyme. Enzymes are proteins that make reactions go faster. The enzymes don't get used up, they just make the reaction go at a faster rate. That's the only way we can get a reaction to go faster. So enzymes will bring the individual reactants together faster than they would normally run into each other. And so we get a faster reaction thanks to the enzymes. Okay, so let's talk, we've talked about chemical reactions and mixtures and compounds. Let's talk about living chemistry. In other words, biochemistry. The chemical reactions taking place inside our bodies. And we can break out chemicals to be considered either organic chemicals or inorganic chemicals. In biochemistry, we have both. The inorganic chemicals are things like water and salts and acids and bases. The inorganic compounds don't contain carbon. Carbon here is key. The organic compounds, the organic molecules are made up of carbon. They have carbon in all of their molecules. So we consider this carbon chemistry. In fact, there's a whole field of what we call organic chemistry, which focuses on nothing but carbon compounds. So the organic compounds are the carbohydrates, the starches, the breads, pastas, sugars, all containing carbon. The fats and the oils, they all contain carbon. The proteins all contain carbon. And the nucleic acids, the DNA, their backbone is nothing but sugars. And they all contain carbon too, as well as the reactive sites on the DNA all contain carbon. So all of these organic compounds are carbon-based, and they are all covalently bonded, and they are all usually pretty large. Like DNA, a DNA molecule, a strand of DNA is about 6 feet long. Yeah, so we have, that would be, if you could stretch it out to its full length, it would be about 6 feet long. And so that is a very large molecule. Now, our bodies need both inorganic compounds and organic compounds to function. We can't have one without the other. So the first of the inorganic compounds is water. There's more water in our bodies than any other inorganic compound. As an adult, our water levels are about 70% of our body. Now, when we get older, an elderly individual would be about 45% water, and infants about 90% water. So we're somewhere, in between those two numbers, probably around 70% water. We use water for everything, for cooling and for solutions and stuff like that. The properties of water: it has a very high heat capacity. It has a high heat of vaporization. It is a solvent. It It can be used for reactions, and it is used in cushioning. What does that mean? Well, the high heat capacity, it has the ability to absorb and release heat with very little temperature change so that our bodies don't fluctuate drastically. As our body gets warm on a hot day, our body temperature doesn't skyrocket. On a cold day, our body temperature doesn't drop and plummet drastically. It takes a lot of heat to get water to change at all. Consider putting water, if you put a pan of water on the stove and turn the heat on, nothing happens right away. It takes time for something to happen to that water. Eventually, you'll start seeing bubbles on the bottom of the pan as the water heats up, and then the water will start to boil. What's happening with the boiling is that the hydrogen bonds holding the water molecules together are breaking apart and reforming and breaking apart and reforming, and the water molecules are getting more active, and that's why the water is coming to a boil as it gets hotter, and you get this rolling boil that you see here. See with a pan like that. That is the heat energy is causing those hydrogen bonds that hold the water molecules together to break apart because they're weak bonds. We also have a high heat of vaporization, meaning that when we get hot, we can sweat and coat the surface of our skin with water. And as that evaporates on the surface of our skin, it cools us down. Heat leaves our bodies when we sweat. And on a hot day, we would sweat to release heat. And we coat the skin with water, and as we release lots of heat, we can vaporize that water. And so we cool down. We also use water as a solvent. All of our solutions in our bodies are based on water. Sodium chloride. Sodium is present in the plasma, in our blood supply and around the cells in the interstitial fluid. Potassium is found inside the cells in solution. The salt content of our body is about 0.9% sodium chloride. We dissolve these salts all the time. We have layers of water around our cells. We have plasma that leaks out of our blood all the time, carrying oxygen, carrying glucose and carrying hormones and other proteins, and the plasma leaks out and becomes interstitial fluid, and those ingredients are absorbed into the cell. Water is our transport medium. It carries the red cells and the white cells and the platelets and the hormones and the proteins and the sugars throughout our body. The liquid portion of our blood is nothing but salt water. We call it plasma. Salts, we use salts all the time: sodium chloride, potassium chloride, calcium carbonate. These will separate into cations and anions. They are ionic. These are ionic bonds. Sodium chloride separates into the positive sodium ion and the negative chlorine ion and goes into solution. Now, chlorine doesn't get to play much. It's just sort of there. But sodium has a major impact on our bodies. It separates into its positive and negative. Sodium chloride separates into its positive sodium, its negative chlorine. We call them, these ions, electrolytes, because they are capable of carrying an electric charge. We have a charge on the surface of our cells. Muscle cells have a resting charge of about minus 90 millivolts. Nerve cells have a resting charge of about minus 70 millivolts, and all the other cells in our bodies are similarly charged due to the presence of sodium on the outside of the cell and potassium on the inside of the cell, or calcium on the outside of the cell and potassium on the inside. These are very important ions that are responsible for giving our cells a charge. So these are called electrolytes. And we need that charge for generating nerve impulses. And we use sodium chloride, calcium carbonate, potassium chloride, calcium phosphates, magnesium chloride. A variety of salts can go into solution and give us the positive and negative ions that we need. And of course, we see right here, here's what happens. Here's one of the reasons why salt goes into solution so easily, because a salt crystal is made up of sodium and sodium and chlorine ions attracted to each other electrostatically like a magnet, if you will. And so they're attracted to each other because they're positive and negative. Well, water molecules also have a positive and a negative end. And the positive hydrogens will grab the negative chlorines, they're attracted to them like a magnet, and the negative oxygen end of a water molecule will grab the sodiums. And you see what's happening here. You see our water molecules, since they're polar, are grabbing the various ions, chlorine ions and the sodium ions, and ripping apart the salt crystal. The salt crystal is the green and gray structure. The crystals tend to be lined up in little rows, just like it shows here. But the water molecule can rip that apart. Salt goes into solution so much easier than sugar does, simply because of the water attacking the ionic bonds. So sodium chloride, we say it disassociates. And all salts are the same way. They're all going to have a positive ion and a negative ion, and they're all going to go into solution very easily, since the water molecule, which is a polar molecule with a positive and negative end, will go after the sodiums and the chlorines. Now that leads us into the acids and the bases. Acids and bases are also electrolytes, because they will disassociate in water too. Just like you put table salt into water, sodium chloride, it will immediately dissolve and separate, with the hydrogens grabbing onto the chlorines and the oxygens grabbing onto the sodiums, and the salt goes into solution. It can carry a charge. The same thing applies to acids and bases. An acid has a positively charged component and a negatively charged component. Acids are what we call proton donors. They give off hydrogen ions. A hydrogen ion is a hydrogen atom that does not have its electron. For example, this is hydrogen right here. It has one proton in the nucleus, and it has one electron out here. It's balanced. It's a hydrogen atom. A hydrogen ion has the proton in the nucleus, but no electron in orbit. So a proton, and we refer to a hydrogen ion, this H+ thing, as a proton, because that's all it's there, is a proton. There's nothing else there. The electron's not there. The electron has been grabbed by something else. We didn't lose the electron. It's just, it has been taken away. So when you take hydrochloric acid, for example, the stomach acid, and put it into solution, it will separate out into its protons and its negative chlorine ion. The hydrogens and the chlorines make up that. And these protons, the number of protons that get released when an acid goes into solution tells you the strength of the acid. Acids give up hydrogen ions. The more hydrogen ions it releases, the stronger the acid is. And in our bodies, we use hydrochloric acid in our stomach, acetic acid, and carbonic acid. Carbonic acid is what we make when we breathe, when we generate carbon dioxide. Let me clear all this. when we generate carbon dioxide from breaking down sugar, the CO2 combines with water in the plasma, because we're carrying the carbon dioxide in our plasma, and that will give us carbonic acid right here. And the carbonic acid makes our blood acidic. And as we breathe out more and more CO2, the carbonic acid levels rise, and that's what tells our brain to breathe faster to get rid of the CO2. So the important acids in our body: hydrochloric acid and carbonic acid. This is a strong acid. This is a very weak acid. Bases are just the opposite of an acid. Remember, an acid, if nothing else, remember this: acids are proton donors. Bases are proton acceptors. They grab the hydrogen ions. They will grab the hydrogen ions. So bases give off what we call the hydroxyl ion. So this is, for example, this is sodium hydroxide up here. Sodium hydroxide is a very strong base. You know, sodium hydroxide, very strong base. It will dissolve your skin. You know, it will dissolve the skin, and you'll. I remember when I was in undergraduate chemistry, that one of the first things they did was, here, hold this. They gave us a pellet of sodium hydroxide, and said, now wait about 30 seconds and rub the palm of your hand, and it would feel slippery because it had dissolved away some of the outer layers of skin, releasing the fats and the oils that were stored underneath, and your skin was slippery. And if you left it there long enough, you'd have a puddle of skin. Well, you wouldn't do that, but it just showed you how powerful it was. Whereas it wouldn't hurt. Whereas an acid will destroy tissue and also cause damage, but it'll hurt. Anyway, sodium hydroxide, when it dissociates, will give you the sodium ion and the hydroxyl ion. Now, those hydroxyl ions will grab hydrogen, grab the protons, and the end result is going to be of an acid will give you water. So an acid and a base together in a reaction will end up giving you water. Combine an acid and a base. The acid's giving off the proton, the base is giving off the hydroxyl, the OH group, and the base will accept those hydrogens, and the end result of a reaction between an acid and a base is going to be water. Think back to the baking soda and vinegar example. You mix baking soda and vinegar together. Baking soda is the base, vinegar is the acid because of the acetic acid. You get the foaming and the gas and everything else, and you get the release of carbon dioxide. You get the release of water, and because the hydrogens and the OH groups are combining, and so you release CO2 and you get water coming off here. You get all that bubbling and everything. So acids will give off protons, and bases will accept those protons. Those protons are going to get accepted by the hydroxyl ions. And in our bodies, we use bicarbonate all the time. And we use ammonia as very powerful bases in our body. Now we can measure the acidity, we can measure the acid base level in our bodies. And I'll tell you that our body tends to want to stay right about a pH of 7.4. So pH scale is a measure of hydrogen ions. pH scale goes from 0 to 14. And we refer to the acid level in our bodies, the acid base level in our bodies. We say the pH of our blood is whatever one. In our case, the pH of our blood, the concentration of hydrogen ions in our plasma stays about 7.4. Now, pH scale measures hydrogen ions going from 0 to 14. It is the negative logarithm of hydrogen ions in moles per liter that ranges from 0 to 14. As a logarithmic scale, each change in pH causes a 10-fold difference. What does that mean? Okay, it means that if you have your scale, the middle of the scale goes from 0 to 14, where 7 is neutral, and if you have a pH of 6, a solution that has a pH of 6 is 10 times more acidic than a pH of 7. A pH of 5 is 10 times more acidic than 6, but 100 times more acidic than 7. pH of 4 is 10 times more than 5, 100 times more than 6, and 1,000 times more acidic than a pH of 7. As you get down the scale from 14 to 0, 7 is neutral, you get more and more as you move down here. The lower the number is on the pH scale, the more acidic you are. The higher the number is, the more basic you are. So each change in a number, either going up the scale or going down the scale, indicates a 10-fold change. pH of 8 is 10 times more basic than a pH of 7. A pH of 9 is 10 times more basic than a pH of 8, and 100 times more basic than a pH of 7. Now, okay, so how does that apply to us? Well, we know that the scale goes from 0 to 6.99 for the acid side. Anything below 7 is acid, anything above 7 is basic. The alkaline side or basic side is 7.01 to 14. Now, hydrochloric acid is somewhere in the neighborhood of 0 because it's very, very acidic. And sodium hydroxide has a pH of 14, so it's very, very basic. Water is neutral. It has a pH of 7. The amount of hydrogen ions at pH of 7 are balanced. There's exactly 7 times whatever times a negative 10th log scale, whatever. So you have an equal number of hydrogen ions and hydroxyl ions at pH of 7. Now, our bodies tend to remain at 7.4, which is slightly alkaline. You can see we tend to stay right around pH of 7.4. And we find that if we get above 7.45 or below 7.35, we get in trouble. Our bodies have a very narrow range that we operate in. 7.35 to 7.45 is that range. We like to stay at 7.4. See, because we're always generating carbonic acid. So we're always making an acid just by breathing. Plus we use acids all the time. We tend to be slightly alkaline so we can neutralize that acid. Our bodies are designed to function in that range. We get above 7.45, cells start having trouble. The cell starts breaking down. The same thing applies at 7.35. In extreme cases, we may see a patient drop down into the 6.9s or 6.8s, and that's a world of hurt. The same thing of even moving up into the pH of 8. Again, that's a very dangerous territory. Cells don't like us to be at that level. If we look at some of these examples, we can see up here is pH of 14 for sodium hydroxide. Down here is hydrochloric acid with a pH of 0. Hydrochloric acid is a very powerful acid. it dissolves skin. It does, you know, when it's not contained, like the hydrochloric acid in our stomach is contained in within our stomach and neutralized by an alkaline layer of mucus, so it doesn't burn our stomach. You know, coffee, pH of 5, for example. Wine, 3.5. Milk, 6.3. You know, all these are different, you know, things that we're all familiar with. Egg whites are slightly basic, pH of 8. Ammonia, pH of 10. Oven cleaner, 13.5. And of course, oven cleaner is usually based off of sodium hydroxide, and pure sodium hydroxide has a pH of 14. We don't like to get into those extremes. We know that they're there, but our bodies like to stay right around this level here. And we work very hard to do that. So, and we don't like these other chemicals to, you know, we don't like to get bleach on our skin or acid on our skin. You know, it's pretty rare that that does happen to us. So, and the acids and the bases in our bodies we contain now. But if we talk about acids and bases in our bodies, we talk about the pH scale, and we try to stay right around 7.4. And if we have blood workup done on a patient, one of the things that you're going to get in the blood is the pH of the blood. That can tell you a lot about what's going on inside your patient's body. If they're too acidic or too basic, we can see what's happening right away. Now, we do like our bodies maintain a fairly constant pH level because we are, anytime we have acids and bases in our bodies, we are busy neutralizing them back to homeostasis. We have lots of neutralization reactions taking place. And every time we have a neutralization reaction, we're going to give off water and a salt. If we were to mix sodium hydroxide and hydrochloric acid together, just like baking soda and vinegar, we get a salt, sodium chloride here, and we get water. When we did the baking soda and vinegar reaction in middle school, probably for our volcano, we were producing water and salt. Somewhere in that water, that liquid that came off the eruption, we gave off CO2 and we got sodium chloride and water. Most neutralization reactions will end up giving you salt and water. Now, we don't usually have sodium hydroxide in our body, but we do have hydrochloric acid. And so we have to neutralize that. And what we do to neutralize the hydrochloric acid is usually something like sodium bicarbonate, but we have our own version of baking soda in our bodies. And what we will generally do is break the hydrochloric acid, neutralize it down to a weaker acid. And we use a system of what we call buffers to break down a strong acid or a strong base. We break them down to a weak acid or a weak base. For example, the primary buffering system in our bodies, and we're going to talk a lot about that in AP2, so don't worry too much about this right now, is the carbonic acid bicarbonate system. And we will use sodium bicarbonate and carbonic acid to neutralize stronger acids, to neutralize them down to a weaker acid or a weak base. So that, you know, carbonic acid and bicarbonate, because we can deal with a weak acid or a weak base a whole lot better than we can deal with a very strong acid or a strong base. And so the buffering system is designed to neutralize acids by releasing hydroxyls, the OH groups, or it can, if our pH goes up, we can release hydrogen ions to neutralize the base. So now, okay, I don't want to get into too much of that because that can get pretty confusing too. So we'll talk a lot more about it and have a better explanations in AP2 in the fall, or and I am going to offer AP2 in May term. I'll just throw it out there right now. Anyway, organic compounds. So the acids and bases were the end of the inorganics. Let's take a look at the organic compounds. The organic compounds all contain carbon. The only exception to this are the two gases, carbon dioxide, CO2, and carbon monoxide. CO is carbon monoxide, and this is carbon dioxide. Now, while they both have carbon in them, they are not organic. They're not organic molecules. They're either CO or CO2, but they are not organic molecules. They are the exception. They are the very small exception to the statement that organic chemistry is carbon chemistry. All the organic molecules contain carbon, but not every molecule that contains carbon is organic. The carbon monoxide and the carbon dioxide are the exceptions. Carbon will, in organic chemistry, carbon will share its electrons. It will never gain any additional electrons. It will never lose its electrons. Remember that a carbon atom will look like this. Here's your carbon atom. It has an atomic number of 6. So it has 6 protons, it has 6 neutrons here, and it has 6 electrons in orbit. It has 2 electrons in its first orbit, and the second shell or second orbit has 1, 2, 3, 4 electrons. But it has room for 1, 2, 3, 4 more electrons. The carbon atom wants to have 4 more electrons so it can be stable. Remember the octet rule that the second shell of an atom can hold 8 electrons? Well, carbon only has 4 electrons in its second shell, and it would dearly love to have 4 more. So it will share its electrons through covalent bonding to pick up more electrons. It loves to do that. That's what a carbon atom will do. It will combine with other atoms. We say it's very reactive. It will combine with other atoms so it can share electrons. You know, it wants to share this electron so it can grab another one. For example, if we were to look at carbon, you know, here's a carbon atom with its 2 electrons in its first shell and 4 electrons, 1, 2, 3, and 4 in its second shell. And here comes hydrogen with its 1 proton and its 1 electron here. Well, now if hydrogen combines with, is covalently bound to the, move this over here, covalently bound to a carbon atom, now they're sharing their electrons. Hydrogen's happy because it now has 2 electrons temporarily in the first shell, and carbon is happy because now it's added another electron here. And suppose it binds to another hydrogen and another hydrogen and another hydrogen, and pretty soon it has 8 electrons in its outer shell, and it's happy. It's stable. The carbon atom is sharing its electrons covalently. It doesn't gain any electrons, doesn't lose any electrons, it's just sharing. And so we see this in all the carbohydrates, we see it in all the lipids, we see it in the proteins and the nucleic acids. And remember that the energy in a covalent bond is based on the number of electrons that are present. It's the potential energy of those covalent bonds. So let's get out of this and go on to Next slide. There we go. Now, we're dealing with an organic compound. It's a polymer, meaning it's a long chain of something. In the case of carbohydrates, for example, it's a long chain of glucoses. Simple sugars linked together. Those are called the monomers. You make starch in a plant by linking together lots of glucoses. In humans, we make glycogen, and we link millions of glucose molecules together to give us glycogen. And so polymers are long chains of something, usually something with carbon in it. Now, carbohydrates are what we use for our fuel source in our bodies. This is the first of the organic molecules. Carbohydrates are made up of carbons and hydrogens and oxygens. They show up in a 1 to 2 to 1 ratio. You have, for every carbon you have, you're going to have 2 hydrogens and 1 oxygen. So that gives you a 1 to 2 to 1 ratio. You should say 1 to 2 to 1. 1 carbon, 2 hydrogens, and 1 oxygen. Carbohydrates always are in this relationship, whether it is sugar or starch or glycogen. It's always a 1 to 2 to 1. Our bodies use glucose. The simplest version of carbohydrates, we use glucose as our fuel. 1 gram of carbohydrates, 1 gram equals 4 calories of energy. And the calories of energy are based on the electrons that are in orbit and covalently bonded or bound among that, within that molecule of carbons and hydrogens and oxygens. So you get a Snickers bar, and this is 180 calories on there. The calories are coming from the potential energy of all the electrons. The ingredients of the Snickers bar has been analyzed at some point, and the calorie content has been evaluated, and it's all added together. So you know exactly how many calories are in a Snickers bar or in a Coke, 220 calories in a bottle of Coke, 60 calories in an apple, about 60 to 80 calories in a potato, 35 calories in 1 Oreo. Just to be fair about different foods. The calorie content is a measure of the available potential energy coming from the food that you're eating. We have a pretty good idea of what all the calorie makeup is on all of our food. Now, we also use sugars in holding together our DNA and our RNA. The DNA structure, you know, the basis for our genetic information is held together by a sugar backbone. It's a 6-foot-long strand, a double strand, and it has a backbone on both sides of the double strand made of sugars. And so we have this 6-foot-long strand of DNA with a sugar backbone. We use that for the RNA also. And those are what we call ribose sugars. There are 5 carbon sugars. Now, the sugar that we use the most is glucose. It's what's known as a monosaccharide. It's 1 sugar. We often call it a simple sugar. You know, the monomer would simply be, you know, glucose is C6, 6 carbons, 12 hydrogens, 6 oxygens, still 1 to 2 to 1 ratio. That's the monomer, a monosaccharide. Glucose or fructose. Now, most of us don't sit around and eat glucose. You know, the sugar that we eat is usually sucrose or table sugar. But we get fructose a lot. If you like a Coke now and then, or a Pepsi or a Mountain Dew or any other good soft drink, the sweetener in most soft drinks like Coke and Pepsi and stuff like that are going to be what we call high fructose corn syrup. It's cheaper than sugar. So the only time you get real sugar in a soft drink anymore is if you have the throwbacks, like Mountain Dew does an original and Pepsi does an original, which is using cane sugar, pure sugar. So we don't usually get glucose in the things we usually, what we get is sucrose. Sucrose, or table sugar, is a disaccharide. It's essentially made up of two monomers. So we have two sugars linked together. Whereas a monosaccharide would be a single sugar like glucose or fructose. The disaccharide is sucrose, the stuff we put in our coffee, the stuff we put in our tea, the stuff that we bake with, the stuff that comes in the little white packets that we at a restaurant or something. That's table sugar. Sucrose, and it consists of two simple sugars linked together. We call it a disaccharide because it has two sugars. Glucose is a monosaccharide, it has one sugar. Now we can store carbohydrates in our body in the form of glycogen. Glycogen is a long chain of simple sugars like glucose linked together, maybe 1 million glucose molecules linked together to give us glycogen, and we store that in our liver. Now, plants don't do that. Plants store their long chains of glucose in the form of starch in their leaves and in their roots. If you eat a potato, you're eating starch. Those are called the polysaccharides because those are many sugars linked together. If you eat an apple, if you eat fries, if you eat a baked potato, if you eat chips of any kind based on potato, you are eating a polysaccharide. You're eating the starch in there. We eat starch all the time in pasta and in breads and rolls and things like that. So monosaccharides, disaccharides, and polysaccharides. Now this is what a monosaccharide looks like. That model that's spinning around there is a glucose molecule. It has 6 carbons, 12 hydrogens, and 6 oxygens on there. And it's arrayed in a sort of a ring structure. So it is not just a straight chain of atoms, but it's formed in a ring. And it has the monosaccharides can either be a 5-carbon sugar or a 6-carbon sugar. The pentose sugars, the ribose and the deoxyribose, show up in our DNA. And in our RNA, the deoxyribose shows up in DNA. That's because DNA stands for deoxyribose nucleic acid, and RNA is the ribose nucleic acid. Those are 5 carbons. And the hexose sugars are 6 carbons. That's what this is over here. Glucose, what we call blood sugar or blood glucose. Fructose, what we find in corn syrup, and galactose, which is just a variation, a slight structural change for glucose. It's a different type of sugar. It has the same properties. It's arranged slightly differently. So these are the monosaccharides. All of our carbohydrates are built off of any one of those 3 6-carbon sugars. Glucose is made from is a 6-carbon sugar. Fructose is a 6-carbon. Galactose is a 6-carbon sugar. Those are the building blocks for all the rest. For example, glycogen, the stored version of the polysaccharide we store carbohydrates in our bodies, is made up of millions of glucoses linked together. So fructose is what we use to sweeten Coke, for example. These are the building blocks. Plants use sugar, use glucose to make starch. They also use it to make cellulose, the woody portion of a plant. So now let's move on here. There's our little spinning glucose molecule again. These are the monosaccharides: glucose, fructose, and galactose. They're all pretty much the same. They all have in their structure, it's just the location of the different molecule, the different functional groups on here. That's what we call these things sticking up. They're all 6 carbons. Fructose is in a pentose shape, but it has an extra carbon here and an extra carbon here, so it meets the definition of a 6 carbon. And there's galactose. You can see that the structure of galactose and glucose are very similar. The only difference is the change here in the hydrogen and the OH group there and on the opposite end. So they're very, very similar. They all have very similar properties. So, but these are the 3 types of monosaccharides. The disaccharides are the double sugars. Glucose can get into the cell, so the cell uses it for energy. Sucrose is too big. Sucrose is a double sugar. It's a disaccharide. Sucrose is going to be glucose and fructose linked together. So that makes it a larger molecule, too large to get into the cells. So the disaccharides include sucrose, which is table sugar, maltose, which is malt sugar, and lactose, which is milk sugar, the stuff that shows up in dairy products. They're all going to be disaccharides. They're all some variation of 2 monosaccharides linked together. And so we see here's sucrose right here, table sugar, which is glucose and fructose linked together. Here is lactose, milk sugar, which is galactose and glucose linked together. And then here is maltose, which is 2 glucoses linked together. So, the 3 sugars that we enjoy as a disaccharide, sucrose or lactose or maltose are all some variation of those monosaccharides linked together. And the last point here, the polysaccharides are long chains of monosaccharides, usually glucose. Plants use glucose linked together in long chains to make starch, and they store the starch in their leaves and in their roots. And we eat that starch as potatoes, or whether it's baking potatoes or sweet potatoes. We eat fries and chips and mashed potatoes and so on. We that is we see the starches in corn kernels and in wheat kernels. We eat breads and pastas and a variety of foods here that all contain starches. Plants use monosaccharides to make starch. Animals, humans, use these monosaccharides to make glycogen. We don't have starch in our bodies. We use glycogen as our source of energy storage. We store our sugars as glycogen, and then we can break down the glycogen when we need sugar to do things. And there's what starch looks like. Bunch of sugars, bunch of glucoses linked together. Here's what glycogen looks like right here. Cellulose, the woody component of plants, is very organized, not like starch and glycogen. And this cellulose forms the fiber in foods, the fiber that our bodies can't process. So, okay, so that's a great place to stop. We can pick up with lipids on Monday. And let me get out of here. Anybody have any questions on any of this? Okay. Will our exams be taken during class? If you want to come in, if you want to take it during the class time, you can. If you're going to take it online, what I'm going to do is usually I'll open up the exam online and let you take it whenever you want. Usually I'll let you take it whenever you want. If you want to take it during class time, that's fine. I generally prefer that you take it outside of the class time because I want to lecture instead. So I'll probably give you several days the test will take you will be 50 questions, and it will take you about 30 minutes to do, and I'll give you like an hour and a half to take it. So so in case you have any problems, not to look stuff up, obviously, but most people get done with the test in between 30 and 40 minutes. And I'll say, okay, I'm going to open it up on a Tuesday morning at 12:01, and I'll close it on Thursday evening at 11:59. I'm just making up those days now, but I'll give you several days to take it so it can fit your schedule, because I would like to, instead of testing during class time, I'd like to lecture during class time. If anybody wants to come in and take it on the ground, let me know and I can arrange that too. So best method for studying for the exam. Let me see all the comments here. Study groups work very well where you're teaching it to each other. The study groups, ways of reinforcing the information to yourself. Flashcards, it sounds like something from first grade, but they actually work really well. If you make your own flashcards, you're going to be writing down the question and writing down the answer, and that reinforces it in your brain, and then you train yourself to the answer. Those are two good ways of preparing for it. The study guide, don't pin your hopes. I shouldn't say, that's not fair. Don't base everything on your studying on the study guide. It has the information in there, but it may not have everything. It should have everything I've covered, but you need to look at the PowerPoints. The PowerPoints and the notes from lecture are really where the test is coming from. The lab test is going to be for the Monday lab. It will be, let's see, Monday lab, we're going to do the skull on Monday. So the Monday lab will have their test open up the following Monday. For the Tuesday lab, it will open up this Tuesday. So that would be the 8th, I think, is when the Tuesday lab test opens up. And the Monday lab will be the following Monday. That will be the 13th, 14th, maybe about, I don't know. I guess I don't have my calendar in front of me, but it'll be the that'd be the third. I guess that'd be the 13th, whatever. So
I think that's
the Monday lab has another week of we have to look at bones, and then look at the skull first, and then we'll have the test. The skull will not be on that test, by the way. So, okay. Is it timed? I have a recommended time limit there. I don't have a hard and fast cutoff on the time. I mean, I can see when you're taking the test, I can see how long you take for the test. If it takes you 8 hours to take the test and you have 110% on the test, I'm going to sort of raise a few red flags about that. But if you take 90 minutes to do 50 questions, that's fine. I'm not going to get upset over that, because some people are going to have test anxiety and they're going to want to do it slowly, and that's fine. So I don't really have a hard and fast on that. The lecture test is going to be on chapters 1 and 2, which is when we wrap up chemistry, you'll have your lecture test on both chapter 1 and chapter 2. The lab test is on unit 1, so it will be on the tissues, the microscope, and mitosis. Tissues, microscope, mitosis, oh, and diffusion and osmosis. That's the lab test. Any other questions? If you have another question, please email me. I don't mind answering questions at all. So, okay. Otherwise, I'm going to get us out of here, and I will see you all next week. So thank you for being here today, and have a good rest of the day.